The next variation on this problem is the boom problem. Remember the boom that I showed you, sort of a beam that was pivoted at one end? So that's actually what we're going to look at here. Let's say that we have a mast of a ship, okay, and there's a boom that's attached to the mast of the ship. And so there it is there. And there's some sort of device here that's holding that in place. Usually it's a lock and pin hinge, something that allows the beam or the boom to pivot in this direction. And let's say that there's a wire that's holding that in place. And there's a kid sitting on the end of the boom, because why not? So there's a kid, right? So here you go. Let's say that the mass of the boom, and they're quite heavy actually. If you've ever, there's a reason why it's called the boom, because this thing not only can swing up and down, but it can swing in and around that mast. And if that thing is just like moving along because of the wind and it smacks you, yeah, boom is really the appropriate word for it. Let's say that this is 50 kilograms. Let's say the mass of our kid is 25 kilograms, and there you go. I'll put a couple of other things on this just so you can see this. So what our question here is, what is the tension in the rope? Okay. Now I'm going to tell you some things about that tension, and we'll kind of go from there. So let's draw a free body diagram and see what's happening here. So let's say that the length of the boom is 4 meters. No, that's ridiculously long. 2 meters long, right? And let's say that this wire here is attached, I don't know, 1.2 meters from the edge. Drawing really not to scale, but there we go. So let's draw in our forces. So if that's true, then here's going to be the weight of the boom to the left of that point. I know the drawing is not that great. Here's the weight of the kid, FG kid. There's the tension, right? Let's say we actually know this angle. I'll call it theta t. And let's make theta t, I don't know, 53 degrees. Okay? So what other forces are acting here? Well, on the boom, there are forces acting here at the hinge. And now let's go back to the swinging bar problem, because technically the boom is a swinging bar. Every time that you have a hinge or some sort of fixed pivot about which something has to pivot around, there's always going to be a component of the force along each axis. Now, the axes that I'm going to choose here are x and y, so that means I'm going to have a pivot force in the x and y directions. But there's a bit of a guess as to what directions they go. But don't worry, you're just going to guess about it, because the math will tell us if we're wrong. So with the pivots, anywhere where there's a hinge or a lock and pin or something like that, we're going to have to make a guess about where the x and y components of that hinge force go. FPX, FPY. Sometimes the books will call these FH and FV for F horizontal and F vertical. Whatever notation you go for, there's always going to be one component in each direction. And we're going to kind of take a guess. So let's just think about this. Knowing that this system is in equilibrium, notice that the tension is going to be pulling to the left and up on this board. And that's actually just physically a true thing about what that rope would do. So what that rope is doing is it's pulling the boom into the mast. Therefore, it would make sense if the hinge force here in the x direction was kind of pushing out. You can almost think of it like a normal force, because that's actually really what hinge forces are, because there's going to be a lock and pin, and the boom is going to be pressed up against that pin in some way, shape, or form, producing a normal force. But we'll just call them hinge forces for now. So I took a guess there, and now I'm going to guess whether or not that is the y component is up or down, and I'm just going to take a random guess and say y is up. FPY is up. But here's the thing, don't worry, because when we put them into our equations, if we calculate the magnitude of these forces to be negative, what does that mean? Hopefully, if you remember in the past, when we calculated forces to be negative, there were kind of two implications. The first was that we put it in the wrong way in our free body diagram, or the second was that that force didn't exist. In this case, if you calculate those forces' magnitudes to be negative, that just means you put them in the wrong direction in your free body diagram. There's no need to redo the problem. You would just analytically state that and off you would go. So the nice thing is the math is going to help us out here. So let's get to this. Step 1, free body diagram. Step 2, axes and declarations. Actually, we also want on our free body diagram, once again, important distances. I've already labeled that one in. Let's just label that in as 2 meters. Step 2, axes and declarations. Let's say up to the right and clockwise are positive. There's nothing magical about that, folks. Actually, technically, let's just do something different. Up to the right and counterclockwise is positive. For no other reason, just for variety. So we know in this step, the next thing we have to do is pick a pivot. So where would we put the pivot point based on what we talked about in the last video? Hopefully, folks, you said here. Now, why would I put the pivot there? Well, that's because I don't know FPY and I don't know FPX. And putting the pivot there means that these two forces are not going to appear in my sum of forces or in my sum of torques equations. And so that kind of like makes our life easier. So that's the reason why we're going to put that there. So next, step 3 in our method, what are we going to do? Hopefully what you said is components, because our tension here does not act along our axes, right? So let's change this into Tx and Ty. But watch what we're going to do here. I'm going to draw in Tx and Ty like this. I'm not going to make a triangle anymore. Why am I not going to make a triangle? Hopefully you said that you're not going to make a triangle because with torques, it's really important the actual point where the force acts. Because if I had put Tx up here, you might have thought that Tx would cause a counterclockwise torque. But look at it here, where I draw it in where it acts, Tx is not going to produce a torque at all. And so it is really important when we're doing components that we put these forces in exactly where they act as I just did. So now, here we go. Any side work? Do I want to do any side work? Actually, I do want to do some side work. I want to calculate my weights. The weight of the beam is 50 kilograms times 9.8 newtons per kilogram, 490 newtons. FG kid is M kid G, 25 kilograms, 9.8 newtons per kilogram. And so that's going to be 245 newtons. All right, so what I always recommend here is do your sum of forces equations first. They're actually quicker and simpler in this, right? So F, sum of forces X, MAX. And so if I look here, I've got FPX minus TX is equal to 0, or FPX is equal to T cosine theta T, right? And then sum of forces Y is equal to MAY. We know that that's going to go to 0. And so I've got TY plus FPY minus FGB minus FGK is equal to 0. Or T sine theta T plus FPY is equal to 490 newtons plus 245 newtons, because we always want to plug in, we can bring the equations down. So what's good about this, folks? Well, what's good about this is if I figure out what T is, I know what FPX is. And I figure out what T is, I know what FPY is. Oh, okay, so that's really good. Because that's actually going to be our secondary objective is FPX and Py, so not just T. But I'm going to leave some space there so that when I'm done with my torque analysis, I can just come back up here and do that work. So here we go. Actually, I don't want my drawing to go too far, so I'm actually going to take out a new sheet of paper, cover that up there, and there we go. So sum of torques is equal to I alpha, and that's about that green pivot. We're not going to be switching the pivot, but I still like to have my nomenclature be clean. So there we go. So let's go through and discover what's causing torques. Well, it looks like neither of these two forces are causing torques. We already discussed Tx is not causing a torque, so it's just the two weights and Ty. It looks like Ty is going to produce a positive torque. If you don't know how to figure that out just by looking at it, put your finger at the pivot and then push the paper like the forces are trying to do it and see what direction the paper rotates. That's really kind of mentally what I'm doing anyway. So I've got a positive torque due to Ty minus torque due to Gb minus a torque due to Gk, and that's going to equal 0 because I know that's zeroing out. So here we go. I'm going to go parentheses, probably bigger than I need it, but there we go. Ty, which is times its lever arm distance, and that's just going to be this horizontal distance because of vertical forces, horizontal lever arm. We said that that acted 1.2 meters away. Let's make this the GB term. We know that FGB is 490 newtons, and then the boom is 1 meter because that's where the center of mass is, and then the kid 245 newtons, and then actually it's 2 meters. Okay, now notice I just put in Ty. Why did I do that? Why didn't I put in T sine 30? Well, coming back over here, I did that because rather than plugging in and plugging back in, having a value for Ty will actually be a little bit helpful later. So I can use Ty to find out what T is, but it's also kind of useful to know what Ty is. So I've got Ty times 1.2 is equal to, that's 490, that's 490, so that's 980. So it looks like Ty is equal to 980 divided by 1.2. Ty is equal to 817 newtons, give or take a little bit of rounding. So there we go. So that's what that is. Therefore, if I want to know what T is, Ty is equal to T sine theta T. 817 newtons is equal to T sine of 53 degrees. So let me just divide that by sine of 53 degrees. And we get that the tension itself is 1,023 newtons. I'm not going to the decimal, it's thousands of newtons, so I don't need to know what the decimal places are on those. And so now we can come back and then finish this problem off. I've got 817 Newton plus Fpy is equal to, and this is 490 plus is equal to 735, and therefore Fpy is equal to, boom, 817. Uh-oh. Hold on a second, did I screw this all up? Ah, no, that just means that, therefore Fpy acts down, not up. And I'm not going to redo the problem. I'm just going to say that I messed things up on my free body diagram. And just that little bit of analytical piece is all I need. And then coming over here, 1023 newtons cosine of 53. I'm not going to have any problems here on my declarations just because of the simple nature of the expression, and that's 616 newtons. So I know exactly what that is. And so there you go. That is how you do the boom problem. Now I can do all sorts of variants on this. Oftentimes I could change the tension. So question might be, well, what would I have to change the tension to make Fpy go to 0, right? You can look at that expression and kind of figure out how that might happen. Or say like at what distance would that have to be placed such that Fpy went to 0, or you know, if the tension had some sort of maximum value, like how heavy could the kid at the end be before the tension breaks? And hopefully if you're thinking about those problems, you're thinking about limits. And that's going to be the problem that you're going to look at later today. Is going to use some of that sort of analysis, but the basic concept of the boom problem is not going to change.